Have you ever wondered how our brains recognize faces or understand language? Our brains are incredibly complex, with billions of neurons interconnected in a vast network. This network allows us to process information, learn from experiences, and make decisions. Scientists and engineers have long been fascinated by the human brain. This fascination has led to the development of artificial neural networks, or neural networks for short. These networks are inspired by the structure and function of our own brains. Neural networks are a powerful tool in the field of artificial intelligence, or AI. They allow computers to learn from data, just like we do. This ability to learn from data is what makes neural networks so exciting. They are already being used in a wide range of applications, from image recognition to natural language processing. Imagine a neural network as a network of roads connecting different cities. Each city is like a neuron, and the roads are like the connections between them. Just like a network of roads can help us travel between cities, a neural network helps information flow and get processed. A neural network is made up of layers of interconnected nodes, which are like the cities in our analogy. These layers are stacked on top of each other, forming a structure that resembles a multi-layered cake. The first layer is like the entry point to our network of roads. We call this the input layer. It receives the information that the neural network will process. This information could be anything, an image, a sound, or even text. The last layer, where our journey through the network ends, is called the output layer. It gives us the result of the network's processing. Think of it as the destination we reach after traveling through the network of roads. Between the input and output layers, we have one or more hidden layers. These layers are where the real magic happens. They process the information from the input layer, much like how we might stop at different cities along our road trip, experiencing something new at each stop. The input layer is the first point of contact for information entering a neural network. Think of it as the gateway to the network, where each node acts like a sensory receptor, much like our eyes or ears. Each node in the input layer receives a single piece of information. For example, if we are trying to train a neural network to recognize handwritten digits, each input node might represent the brightness of a single pixel in the image. So, for a 28 by 28 pixel image, our input layer would have 784 nodes. The input layer doesn't do any processing itself. Its job is simply to pass the information onto the next layer, the hidden layer. It's like the entrance to a museum. It just lets you in. The real exploration starts inside. The number of nodes in the input layer depends on the type of data being processed. For example, if we are processing images, the number of nodes will depend on the resolution of the image. The more pixels in the image, the more nodes we need in the input layer. The hidden layers are where the real magic of neural networks happens. This is where the network processes the information, much like how our brains process information from our senses. Each hidden layer can have multiple nodes, and each node receives input from all the nodes in the previous layer. Each node in the hidden layer performs a simple calculation. It multiplies each input by a corresponding weight, adds a bias term, and then applies an activation function. Think of the weights as adjusting the importance of each input, and the bias as adjusting the overall level of activity in the node. The activation function is a mathematical function that introduces non-linearity into the network. This is important because it allows the network to learn complex patterns in the data. Without the activation function, the network would just be a linear model, which is not very powerful. The number of hidden layers and the number of nodes in each layer are important parameters that affect the network's ability to learn. More layers and more nodes generally allow the network to learn more complex patterns, but also make the network more computationally expensive to train. Section 5, the output layer, revealing the results. After the information is processed by the hidden layers, it reaches the final destination, the output layer. This layer is like the display board of the network, showcasing the results of the entire journey. The output layer provides the network's prediction or classification based on the input data. The number of nodes in the output layer depends on the task at hand. For example, if we are trying to classify images into categories like cat, dog, or bird, our output layer would have 3 nodes, one for each category. The node with the highest activation value would then correspond to the network's prediction. The output layer is where we can see the fruits of the network's labor. It's the moment of truth where we see if the network has learned to recognize patterns and make accurate predictions. Section 6. How neural networks learn, a simplified view. Now that we understand the basic structure of a neural network, let's try to understand how these networks learn. The learning process of a neural network can be compared to a student learning a new subject. Initially, the network's weights and biases are randomly assigned. This is like the student starting with no prior knowledge of the subject. As the network processes more and more data, it uses a process called backpropagation to adjust its weights and biases. Backpropagation is like the student receiving feedback on their performance. If the network makes a mistake, the error is calculated and propagated back through the network. This error signal is then used to adjust the weights and biases so that the network is less likely to make the same mistake again. This process of forward propagation, error calculation, and backpropagation is repeated many times with different sets of data. Through this iterative process, the network gradually learns to make more accurate predictions. Section 7. Types of neural networks. A glimpse into diversity. Just like there are different types of students with varying learning styles, there are different types of neural networks, each specializing in different tasks. Some common types include 1. Feed-forward networks. These are the simplest type of neural networks where information flows in one direction from input to output, without any loops or cycles. They are often used for tasks like pattern recognition and classification. 2. Convolutional neural networks, or CNNs. These networks are designed specifically for processing images and other two-dimensional data. They use specialized layers called convolutional layers to extract features from the input data. CNNs have revolutionized the field of computer vision and are used in applications like image classification, object detection, and image segmentation. 3. Recurrent neural networks, or RNNs. These networks have a unique ability to process sequential data such as time series data or natural language. They have connections that loop back on themselves, allowing them to retain information from previous time steps. RNNs are used in applications like language translation, speech recognition, and text generation. Section 8. Real-world applications, neural networks in action. Neural networks are no longer just a theoretical concept confined to research labs. They have entered the real world and are being used in a wide range of applications, transforming various industries. Let's look at some examples. 1. Image recognition. Neural networks are the driving force behind many image recognition applications, from tagging friends on social media to enabling self-driving cars to see their surroundings. CNNs in particular have achieved human-level accuracy in many image recognition tasks. 2. Natural language processing, or NLP. Neural networks are helping us understand and generate human language like never before. They power applications like virtual assistants such as Siri and Alexa, machine translation like Google Translate, and sentiment analysis for understanding customer reviews. 3. Medical diagnosis. Neural networks are assisting doctors in diagnosing diseases earlier and more accurately. They are being used to analyze medical images like X-rays and MRIs, identify patterns in patient data, and even predict the likelihood of disease progression. 4. Financial predictions. Neural networks are used in the financial industry for tasks like fraud detection, risk assessment, and algorithmic trading. Their ability to analyze large data sets and identify complex patterns makes them valuable tools in the world of finance. Section 9. Conclusion: the future of neural networks. Neural networks have come a long way since their inception. They have evolved from simple models to complex architectures capable of solving real-world problems that were once considered the exclusive domain of human intelligence. As research in neural networks continues to advance, we can expect to see even more innovative applications emerge in the future. Neural networks have the potential to revolutionize healthcare, transportation, entertainment, and many other industries. However, the development of neural networks also raises ethical concerns. As these networks become more powerful, it's important to ensure that they are used responsibly and for the benefit of humanity. Understanding neural networks is not just about understanding a technology, but about understanding the future of intelligence itself. As we continue to unlock the secrets of the human brain and translate them into artificial systems, we are embarking on a journey that will redefine our relationship with technology and shape the future of our world.